Swayam Prabha. Digital India. Educated India.
Good morning, and this lecture what we are going to look at is some graph algorithms in streaming model. Okay. So, you have been looking at streaming, there are some input elements, packets coming, and you need to compute something, right, number of distinct elements or number of elements, or do some sampling, and the space was a big criteria, and you are doing it in small space. In particular, ideally polylog space, right, log n or log n or polylog. That was the kind of things we have seen. So, today our object is going to be a graph, and the vertices, let us say it has n vertices. Everybody knows, my algorithm knows, and it is told in advance, and then edges are coming in the stream. Okay. So, that is the model we are going to have. There are n vertices, n is known, and edges are coming, and as and when edges come in this graph, I have to solve some questions, some natural graph questions. Okay. One by one. So, when the new, so there we are trying to solve some problem. Let us say you want to find the shortest path between a pair of vertices or something. That is a query you want to answer. When a new edge comes, you update your graph, and then you should answer the question. Okay. And the time is take to answer the question is a secondary thing. We are, in fact, you can worry about it, but in this lecture we are not going to worry so much about it. We are going to worry only about the space. Okay. How much space you are going to use to store your graph or whatever, some subgraph or whatever information you need to answer the question, you are going to store that, and you want to talk about the space to store that graph. Okay. Now, how do we represent a graph? Adjacency matrix or adjacency list, right. So, these are two standard ways to represent a graph. How much space does it take? Okay. So, suppose number of edges is m, right. This is a changing thing, because as the edges come, your m is going to increase. Adjacency matrix takes how much space? N square bits, and adjacency list will be m plus n in the order of that many cells. Now, each cell is some sort of a pointer or an address in the range 1 to n. So, I will add some log n bits for it. So, I am going to say it is something like m plus n okay. Now, since I said that time to compute solve your problem is not going to be important, one possible way is to just store the whole graph, right. Whenever new edge comes, update it, store your graph, and whatever time it takes to solve your problem, answer that. Okay. Now, that space is going to be like either n square or m plus n log n, and our goal in this is to do it with preferably much less space. Okay, so I want to do much less than n square or much less than m log n bits. Okay, and it turns out most of these problems are hard. That there are very few problems where you can do anything substantially better than m log n bits. And tomorrow, next week, Deepak will have a session on lower bounds for these space in graph streaming, where you will say that there are a few problems you cannot do in less than so much space. Okay, so but there are a few problems where you can do slightly better than m log n bits, and that's the kind of 2-3 problems we are going to look at today. Okay, so goal again, unlike the kind of algorithms you have seen where we were trying to do it in polylog space, right? Here, even something like n log n bits is good for us because that's the best you can do. Okay, we are just trying to beat n square or trying to beat m log n. So, we will have schemes where the space used will be like n log n, and it will be complemented by some lower bound next week. So, we are deviating from this polylog requirement, and here we are talking about subquadratic. Okay, we are just going to settle for something like that. That's all. Okay, so let's get started with problems. So, the problem 1 I want to talk about is this Boolean question: is G connected? Okay, so now without the streaming constraint, in the classical world, if I give you a graph, how do you check whether the graph is connected? Yeah, connected means what? There must be a path between every pair of vertices. So, how do you check? Hmm? Hmm. Okay, that will only tell you about a pair of these vertices. I want a path between every pair of vertices.
Every vertex is one by one, which is of every one vertex at a time. Check if there exists a path with that vertex to every other vertex.
How do you check that? Okay, so I forgot to say we are working in undirected graphs. Okay, of course we can also talk about directed graphs, but today we are going to be talking only about undirected graph. Yeah, BFS, right? BFS, DFS are precisely graph exploration techniques to check whether check for paths. So, you just start at a vertex, grow a BFS, and at the end of it, if you can reach every vertex, you know that graph is connected, otherwise it is not. Okay, fundamental algorithmic question, and that is what you can just do a BFS and check. Okay, so that is without worrying about streaming. And how much time does that take? BFS, B plus E, so or M plus N. If there are M edges and N vertices, in linear time, you can check whether the graph is connected using BFS or DFS. Okay, so now, but now we have to sort of switch gear, and we are looking at a slightly different model. We have to maintain something so that when a new edge comes, we will be able to answer whether this current graph is connected. So, how do we maintain? What do we maintain? That is the question, right? And because the space is a constraint for us. So, what do we maintain so that, and what sort of update you will do when the question, when an edge comes to answer this question? So, I have a current graph. Some snapshot of the graph I want to maintain, because I can't store the whole graph, that's going to take me a lot of space. So, some snapshot I will store, some fingerprint, something, and when the new edge comes, I will do some query on this and answer whether the graph is connected. So, I want store enough to be able to answer this question. Store a pair of vertices that are not connected. So, there may be several pairs, right? Okay.
An incoming edge is kind of connecting with any of the pairs.
Okay. So, one idea what she is saying is store all the pairs between which there is no path. But that's like could be as bad as n choose 2, right? Incidence matrix. Okay.
Create the what is it is connected to the path. Let's say at the moment of T, we have a section. Some vertices are not connected.
So okay, let me ask this question. So maybe the graph is not connected at this point, but when that new edge comes, the graph becomes connected. Then what is that new edge doing? Yeah, I'm a little better. Yeah, sort of creating a path. Yes, but so at this point the graph is not connected. So I have at least two components, and when the new edge comes, the graph becomes connected. So what is the edge doing? The edge is doing something. What is it doing? It's connecting these two components, right? So let's say I have maintained the graph is not connected, so I maintain two components. And what do I maintain? I maintain the set of vertices in each of these components. Okay. You said every pair of vertices which are not connected, some thing like that is what I'm going to store, but but I there are some pair of vertices which are connected. So somehow there is some sort of an equivalence class of all these vertices that are in one component. Here is a set of vertices that are in another component, and I store these equivalence classes or store these sets, and then when an edge comes, what do I check? Whether the endpoints are whether the endpoints are in the same component or a different component. If it's the same component, that's not useful to me, I just throw it away. If it's connecting two components, I'll add that edge and then update my structure. So what I'm going to store, so the solution store a spanning forest. Okay. So what that means is that here is a set of vertices which are connected, here is another set of vertices which are connected, here is another set of vertices which are, and so on. So this is what I store. Okay. What do I not store? I mean why is this a subgraph of the graph? Because there may be edges in the same component forming cycles which I don't store because I don't need to. Okay. So all I am going to store is essentially sets of vertices in each connected component. That's my data structure, if you like. Okay, that's my data structure or what I'm going to store. And now the algorithm is so with edge E comes if E equal to UV and U and V are in different components. Okay, so I maintain a set of edges, let's say F. okay, which is initialized to empty set. I start with nothing, then that's all. So what am I storing? I'm storing a set of edges in a spanning forest of the graph. Okay, and when a new edge comes, I check whether the endpoints are in different components. If so, I will add it to my collection of edges. Otherwise, I just discard it. Okay, that's my algorithm. Well, I have to answer whether the graph is connected or not. When is the graph connected? Number of components is 1. How do I even figure that out from what I store? U and V. Yeah, but so there is no finally, it goes on forever. Okay, so at some point there is the edge comes, I update my structure, and now I have to tell the user is waiting. I have to say whether the graph is connected or not. Okay, so he's right. If the number of components is 1, I know the graph is connected, but I'm not storing enough information to say. All I am storing is a set of edges. So when is, yeah, all the vertices are in the same component. Yes. Cardinality of f equal to, should it be n or what is it? That's the correct direction. N minus 1, right? So if cardinality of f is equal to n minus 1, then return yes. Why is that? What is the graph theoretic property you are using? Not minimum spanning tree, any tree. Any tree on n vertices, has n minus 1 edges, right? Because there are n vertices and I am storing this forest. As long as it's a forest, it's going to, I mean, it has more than one component, the number of edges will be less than n minus 1. The moment I have one component, because I am always storing a tree, the number of edges will be n minus 1. So let me just put this lemma, which could be discussed in the tutorial again if you have not seen it. Any tree on n vertices has n minus 1 edges. What is a tree? Acyclic and connected acyclic graph, right? If it's not connected, it's a forest. So a connected acyclic graph is a tree. That's the definition of a tree for us. Prove that any tree on n vertices is n minus 1 edges. Okay. If you have not seen it, it's an interesting, it's a very basic theorem in graph theory, and if there is time, you can look at it in the tutorial. Okay. Okay, so my structure basically stores a collection of edges of a forest, and so all I'm saying is you don't need the whole graphs. In particular, for each component, I just need a spanning tree. I don't need the edges not in the tree in this component. I don't have to remember them, because for the purpose of answering this connectivity query, all I care is this set of edges. I don't need the other edges. So that's the saving I do. Okay. So how much space do I use? Because I said space is the important thing. That's what we care about. Because f stores some edges. That's my only storage. Okay. And each edge is basically 2 endpoints, and each endpoint is a number between 1 and n. So it takes about log n bits, and I store at most n minus 1 edges, because the moment I have n minus 1 edges, I know there is one component. I can keep on saying that the graph is connected for any other edge that comes. Okay. So the space is Questions? Okay. Now, you can talk about what in the stream I am asked to delete edges. Okay. This thing doesn't work anymore because I'm not storing enough, because if I store, let's say in one component I stored some tree, and the algorithm is asking me to delete these two edges, I am not sure that this component is broken. Why not? Because I did not store some edges, remember. So there are other edges which I did not store, they may be connecting these two pieces, right? Because there may be an edge like this in the graph which I did not store it. So if I want to do deletion, the whole it's a lot more complicated problem, and that's for another lecture or more research direction, I would say. Okay, so you're only talking about insertion only tree. So you have to, it's a really interesting problem, very complicated. It had a long history of some 10 papers written on that. If I also allow deletion, how much space, what structure do I use, and so on. Okay, so let me make a note. We're doing only insertion. So, in the data structures course, maybe you will actually look at how, how much time it takes. Like I said, we don't worry about time here, but you can ask, how quickly can I check whether the two endpoints are in different components or not. Okay. So, people have seen an advanced data structures course who would recall that this is the set union, this, find union find problem, right? You want to maintain a collection of sets such that you want to know given an element, what set it belongs to, and given a pair of sets, I want to merge them. I want to do a union of these two sets. Okay, how efficiently can I do? There are very interesting data structures for that, but we won't bother about it, because as I said, time for doing this is not our current concern now. Okay. Okay, that's the end of connectivity question. Any question? Then I move on to a different problem now. Okay. Let's say I want to check whether the graph is bipartite. Okay. So what is a bipartite graph?
Vertex can be partitioned into two sets such that no vertex between the same set has any edges.
No edge is in the same set. Right? There is a way to partition the. How many people have heard of this bipartite graphs? Okay. So you can partition the vertex set into two parts such that there are no edges within each part. Okay. This bipartite graphs come up in real world applications many times, because you're talking about men and women, or machines and jobs, and resumes, jobs. There are all kinds of problems where your graph has a natural two parts where each part has no edge. Okay. So now here is this question, and it's also known as two colorable, right? I.e., we can color the vertices of the graph such that whenever there is an edge, the endpoints get different colors. Okay, so if it's bipartite, you can color one part as one color, another part as other color, and since all the edges are going across, the endpoints of every edge gets different color. Any characterization for bipartite graphs? Yeah, what is that? What?
If it has a cycle, it is a odd number of edges.
it should be a odd length. The connection to odd cycle is correct, but so what a graph is bipartite if and only if number of edges in a cycle. So let's look at an odd cycle. And let's see whether I can properly two color this, right. Suppose I give color 1 to this vertex necessarily gets color 2, this should get color 1, this should get color 2, and I am stuck here. I can't color 1 or 2 because it has neighbors in both sides. Okay. So an odd cycle is clearly not bipartite, and it turns out that a graph is bipartite if and only if there is no odd cycle. So if there is an odd cycle, you have a problem. Here is a proof, and it turns out the converse is also true. If there is no odd cycle, then you can happily partition the vertex set into 2 and make it 2 colorable. Okay. So this is again another interesting. Okay. So graph theorists will see a lot of interesting exercises here. Okay. So, okay, so let's again go back to our classical world, no streaming, nothing. Given a graph, how do I check whether the graph is bipartite? Okay, so you've seen it or not? Some of the third year undergrad Shastra guys. Have you not seen it in your algorithms course, graph algorithms or graph theory, discrete math? So how do you check whether a graph is bipartite? Well, sort of you can do a BFS, start from a vertex, color it 1, color all its neighbors 2, and the neighbors 1, neighbors 2, and so on and so forth. Okay, so basically grow a BFS starting at a vertex, and whenever there is an edge where both endpoints are in the same level, then it turns out you can extract out an odd cycle out of it, and otherwise this coloring is nice and proper to coloring. Okay, so you can again just with BFS and little more checking in order m plus n time, you can check in order m plus n time. Okay, now let's come back to our streaming problem. Edges are coming. What do I store so that when a new edge comes, I can figure out whether or not it is bipartite. Okay. So let's come back to this sort of solution we had for connectivity. So again, time is not such an issue for us, as I told. So suppose I maintain this spanning forest, let's say, and then when an edge comes, if it connects two components, I will add it, no problem. But if it connects, if the endpoints are in the same component, I can't just discard it, I need to do something, right? What do I need to do? Check whether in that component there is whether it forms an odd cycle, that's all. That's all. There's nothing really much more than what we are doing here. I'll say and maybe argue why that's enough. So solution again here is store a spanning forest. So start with the edges currently in the spanning forest, and when the edge E comes, check if F, well, if E joins two components, then F is F union E, because no problem, it is connecting two components, so it is not going to even form a cycle, forget about even forming an odd cycle. So, I will add it to my collection, and so now I have again a spanning forest of the original graph. But if E joins, okay, if the endpoints of are in the same component, then I have a check now. If F union E as an odd cycle, return no, else return yes. In either case, I am not adding the edge E. So, always I maintain the spanning forest. So, when the new edge comes, if it connects two components, I will add it. If it connects, if the endpoints are in the same component, then I know that it is not adding anything more to the connectivity, because the component, it is already in the component, but it may create an odd cycle, which I will check. How do you check? Well, how fast can you check is an interesting question, but I am not going to worry about time. So, you can do whatever the algorithm I said, do a BFS and check, and if it forms an odd cycle, then you report that it is not bipartite, otherwise it is bipartite, and either way I discard that edge. And the claim is that this is good enough, that if the algorithm returns it is bipartite, then it is bipartite, even though it is not storing all the edges of the graph, okay, because the external other edges can only form an even cycle with whatever you have stored, and so the graph will be bipartite. So, the space again is like before. So, let me again remark here, how fast can you do it? It is an interesting secondary question. There is another algorithm for checking bipartiteness. I will mention that again. It is based on a black box graph theory theorem, nice theorem, I would mention it. So, another structure, another algorithm. So, given G, let G prime, I am going to construct so V prime has two copies for every vertex. For all V in V, and E prime equal to U1 V2 comma V1 U2 for all UV in E. Okay. So, let me draw an example. Here is my graph G. So, my G prime has two copies of the same vertex set, and whenever there is an edge U comma V, this U1 will be adjacent to V2 and this V1 will be adjacent to U2. So, this is my G prime. Okay. Is there a name for this graph? Product something. So, for example, if G is like this, then I will have A1, A2, B1, B2, C1, C2, D1, D2. Every vertex is copied. And since there is an AB edge, it will have A1, B2 and B1, A2. AD edge will be like BC edge will be and CD edge will be like this. And here is the interesting claim left as an exercise, maybe can be done in tutorial. G is bipartite if and only if G prime is not connected.